Hi, I'm Louis Wagasback, Thermal Analysis Product Manager at TA Instruments. I'd like to welcome you and thank you for joining us for today's webinar. During the webinar, you can customize your viewing interface by arranging windows to your liking. You can resize the video and slide windows independently from one another by clicking and dragging the bottom right corner of each window. If you get disconnected at any time, please use the instructions you've received to log back in. You can access several different content windows by clicking the widgets at the bottom of the screen. These include speaker bios, additional file downloads, and social media interactions. If you need help, click the question mark widget. Please ask any questions you may have at any time during this presentation by submitting them through the Q&A window. We will answer as many of these as possible at the end of the webinar. Our guest speaker today is Roger Blaine. Dr. Blaine holds a PhD in analytical chemistry from Oregon State University. Roger has over 100 publications on the applications of thermal analysis. He is a founding member of the ASTM International Committee on Thermal Analysis and the Thermal Analysis Forum of the Delaware Valley. Roger is an emeritus member of the North American Thermal Analysis Society, having served as its president, vice president, secretary, and treasurer. Roger retired from TA Instruments after 40 years as principal scientist. He currently serves as a consultant for thermal analysis standards and regulatory affairs. The title of Roger's presentation today is an introduction to lifetime testing by thermogravimetry. Roger?
Thank you, Louis, and thank you for joining us here today. Today we're going to be talking about lifetime testing, and particularly the mode of testing for lifetime using thermal analysis, and in particular thermogravimetry. Our purpose here is to cast lifetime testing both with regard to its position in history, where we are today, and if we have a few moments, we'll talk a little bit about what the future for this technique may be. But to begin our discussion, we need to have an understanding of the definition of what is lifetime. Lifetime is an estimate of how long a product will last. You may be familiar with a number of examples of lifetime testing. When we buy an automobile, our warranty for that product is expressed in years and in miles. A typical warranty might be 50,000 miles or 5 years of service, whichever comes sooner. In scientific test equipment, furnaces for thermogravimetric analyzers, for example, are often warranted for 1 year of service. This again is an estimation of lifetime. But for many products, such as bridges, roads, nuclear power plants, the length of time of service is much longer. It can be as much as 30, 40, or 50 years. Our challenge is how to estimate the lifetime for a product into the future, which may contain materials that we have not been around for the length of time that we anticipate them to be used. So we perform something that is lifetime testing. This is a process whereby we estimate how long a product will last by its performance in an accelerated test. We select some value in lifetime testing, we select some value to indicate the end of life. We'll use an example of a light bulb. A light bulb is either on or off, and if we turn the power on, we anticipate that it will actually go on. If it fails to go on, if the filament is broken, the light bulb fails. So our test for a light bulb is whether it is on or not. Then we repeatedly stress representative examples of these products, a series of light bulbs in our example, and for the length of time at which they last. And then we'll achieve some average value for the series that we test and compare that value to what we would anticipate would be the normal use. For example, in the case of light bulbs, we might test 10 such light bulbs for its lifetime. At least one of the light bulbs will be the first one to go out, and one will be the last of the light bulbs to go out. But if we test 10, we can select the point at which 50%, that is half of the light bulbs, go out, and we'll use that as the test time, estimated time. Now, if we turn our attention to the packaging for a light bulb, you can tell by the color of this carton that it's a little bit older type, but on this carton, the lifetime for this particular light bulb is estimated at 1,200 hours. Particularly with the advent of the longer lived bulbs, this time has been modified so that we divide the actual on time for the light bulb by 3 hours per day to come up with an estimation of the life for this light bulb of about 1 year. This is an example of accelerated testing. Now, in the 1930s and 40s, the electrical industry was the industry that most used estimations for lifetimes. And the folks in this trade found that many of the electrical components, like transformers, for example, shortened their lifetime under service. That is, as they were in use, the temperature of the product would go up, and with the temperature being elevated, the lifetime would go down. So we observed that there was a relationship between lifetime and temperature. This concept was put to the advantage in the form of what was called oven aging tests. In oven aging tests, products like wire insulation or the actual polymer itself that might be used for the wire insulation were placed in ovens, and these ovens were elevated in temperature. A series of ovens that were about 10 degrees Celsius apart, numbering 4 or 5 ovens, then would be used to test the particular products. And once again, we would select the criterion of 50% failure. We would test a series of products. We would obtain the value for 50% failure at each of the ovens. That time and temperature relationship permitted us to plot the logarithm of the lifetime versus the reciprocal of temperature. And this created a curve from which we could extrapolate to other times and other conditions. These tests often took about 2 years to perform, even though they were accelerated in nature. And then there was often another 2 years for this data to be evaluated. But this gave us a tool then for estimating lifetimes at long times, but at the ambient temperature at which they're to be used. Now, the challenge with oven aging tests were that what was the criterion that we selected for our failure? In one case, electrical insulation, it might be just the point at which the polymer started to leak electrical power across the insulation. But it could be some other testing, such as mechanical testing. We might look at a material and gauge its end of lifetime by 50% failure rate. It turned out that the various oven aging tests that we examined, each of the test results, each of the tools that we chose for a lifetime, gave a somewhat different value. And so we cannot substitute one lifetime testing for another, or more properly, we have to realize that there is a range of lifetimes depending upon use. Now, the relationship that was derived by the oven aging test is shown here. And I don't mean to be too mathematical here, but we have to think about the concept of lifetime as a kinetic process, and kinetics are described in mathematical pathways. So in this example, we have the logarithm of the time to failure, logarithm of time on the left side of the equation, and on the right side of the equation, we have a reciprocal temperature. This equation is a form of a straight line. Y equals the slope times the independent variable plus a constant. So in this profile, if we were to plot the log of time versus the reciprocal of temperature, E over R would be the slope and C would be the constant. This is the relationship we're looking for. Now, in the 40s and 50s, Underwriters Laboratory began to formalize this process. Again, their primary aim was the electrical industry, but a series of tests became very common. Impact testing, mechanical testing, and electrical testing became very popular. They initiated the formal oven aging tests, and these the results of these oven aging tests began to be incorporated into Underwriters Laboratory, ASTM, and other electrical standards. The Underwriters Laboratory also initiated the terms for terms such as thermal index and relative thermal index. Excuse me here. These two terms, thermal index is the term that is meant to be the amount of time that a product will last given a specific set of experimental conditions. And so it's often expressed as a temperature like 200 degrees Celsius for a 2,000 hour lifetime. And the second term that we run into is relative thermal index. This is a similar value, but in the relative thermal index, our given results for a material are compared to a reference material. That's the relative portion of the thermal index value. Now, a moment ago, I mentioned that there were a series of experimental conditions that could change our estimation of lifetime. We have here one such example. This is a polyethylene terephthalate, a material that is used that has been subjected to lifetime testing. And we have a series of these lifetime curves generated, but each one is at a different humidity. Polymer scientists know that polyester, that is polyethylene terephthalate, is particularly susceptible to degradation by moisture. And in this example, we see that at 20, 50, and 100% humidity, the lifetime for this product changes. So this illustrates the concept that lifetime itself is not a fixed value. It can change based upon our test conditions, and it can change upon the choice of the end of lifetime that we select. Now, in the 1970s, the oven aging test had been incorporated into standards, as we've already talked about. But to generate the lifetime values took often 2 years of experimental time, plus another 2 years for the evaluation of the results by the regulatory agencies. So this meant that if you were bringing a new product to market, there was the opportunity for a 4-year delay before you could estimate its lifetime. And by then, a necessary condition for an engineering plastic. The need became apparent then for what was called an accelerated lifetime test. And in those days, Larry Green and John Blair of DuPont Company, a large polymer manufacturer, came to their Instrument Products division, which later became TA Instruments, and asked if thermal analysis might not be a tool that could be used to accelerate the estimation of lifetime. This was required because even very small changes in polymer composition, which were very unlikely to change the physical characteristics by much, certainly the lifetime by much, would require these long, elaborate tests. For example, if you had a filled polymer and you wanted to go from 35% filling to 30% filling, recognizing that the filler was inert, you still had to retest the product. And while the modulus of the material might change slightly based upon this small change in filler content, the actual lifetime of the product was unlikely to change. And so some form of accelerated testing became a request. And what was driving this, of course, was competitive pressures. If you had a new, better, more inexpensive product, you wanted to come to the market and capture as much of that market as you could, as early as you could. This request happened at about the same time that a series of advances in lifetime testing were being done. In 1948, Thomas Dakin of Westinghouse in Pittsburgh, Pennsylvania, made the postulate that certainly for polymeric materials, lifetime was probably due to decomposition, and decomposition was a kinetic process. Kinetics was defined by the Arrhenius equation, which was developed in the 1890s. And when that was coupled with the law of mass action by Goldberg and Vaga in the 1840s, we developed the concept of the general rate equation that is commonly the basis for kinetic measurements. But the concept that Dakin had that there was a relationship between lifetime testing and kinetics was groundbreaking. It now meant that we had a theoretical basis for the empirical relationships that had already been developed. In 1966, Joe Flynn and Leo Wall at what was then the National Bureau of Standards developed a quick and easy method for determining kinetic parameters from thermogravimetric data. This work was later observed to be very similar to the work of Takeo Ozawa at the Thermotechnical Laboratory in Japan. And so this method has become known as the Ozawa-Flynn-Wall method. But its ease of use by handheld calculators made it a popular tool for kinetic determination as early as the 1970s. In the late 1970s, Krzyzanowski at the Electrical Institute in Czechoslovakia, now the Czech Republic, created the relationship of being able to determine thermal indexes from the thermogravimetric data. In the early 1980s, Larry Green and John Blair of DuPont began to request the concept of accelerated aging tests based upon thermogravimetry. And in the early 1980s, TA Instruments and other suppliers began to bring to the market computer-based data analysis that made kinetic determinations a tool that could be used by those of us less skilled in the art. In 1994, ASTM International publishes the first standards for thermogravimetric-based kinetics in the form of standard E1641, and shortly thereafter, the measurement of thermal endurance, another phrase for lifetime based upon standard E1877. Now, the Flynn and Wall procedure is based upon a variable heating rate approach. That is, we take a series of test specimens, in these cases polymeric materials, we cryoscopically, that means in liquid nitrogen, grind them so that they are small particle sizes. We then take a test specimen of about 10 milligrams, pardon me. We then take a series of specimens of about 10 milligrams, 4 or more of these, and test them in a thermogravimetric analyzer for their decomposition temperature at a series of heating rates ranging between 1 and 10 degrees Celsius per minute. Now, as the heating rate increases, the temperature of the decomposition also increases. This permits us to look at the mass loss for the material, find a point of constant conversion. In this case, we commonly use 5%, and select that temperature at which that 5% portion of the weight loss curve is created. So on this curve, you see the line represented by 5%. Where that crosses the individual curve, that temperature is taken. So we have a temperature and a heating rate as our experimental data. The value of 5% was taken largely for two reasons. The first of these is that many polymeric materials have a certain amount of volatile content. For example, nylon can absorb from atmospheric air about 3% moisture. So if we're looking at the decomposition of the polymeric material, we want to be at some weight loss that is above the evolution of the adsorbed moisture, but early on in the decomposition pathway. 5% was arbitrarily chosen for these values, and most lifetime testings by thermogravimetry today is done with a 5% mass loss as the point of constant conversion. So I mentioned that from this kind of a curve, we gather a temperature and a heating rate profile information. We then plot our curve on the y-axis, where heating rate is displayed on the y-axis versus the absolute temperature on the x-axis. And when we do this, we get a family of curves at each conversion level, such as the one that you see here. On the far right-hand side, we have the conversion level for the profile at a 0.5% point of constant conversion. On the left-hand side, we have the curve for 20% mass loss. And you see that and in between, of course, are the intermediate values. But you see that the last 3 or 4 curves on the left-hand side all have a similar slope. This means that they have the same chemical reactions being involved and that they are consistent in their activation energy. While the term on the right-hand side, the 0.5% conversion, has a different slope altogether. And this is a demonstration that its mechanism, its mass loss region, is different than the others in this curve. And you can see that right there at the middle of the profile is our 5% mass loss region. And once again, we now have experimental data to support the concept of 5% conversion as our point of end of life. This series of equations this equation shows the Flynn and Wall variable heating rate value. On the left-hand side is the slope of the curve of that line we saw just a moment ago, a change in the log of the heating rate. And on the right-hand side, we have the change in the log of the reciprocal temperature. Again, we have an equation that is in the form of a straight line. Y equals the slope times our independent variable plus a constant. And the slope in this curve is, is the activation energy E divided by the gas constant and inclusion of a term A, which is the derivative of a mathematical approximation called the Doyle approximation. And the Doyle approximation is lifted from the literature. The activation energy determined by the process that we just described can be used in this equation, the one from Krzyzanowski, where the thermal index is related to activation energy, some time, which is the estimation time that we might choose, such as 60,000 hours or 100,000 hours, the gas constant, and one heating rate example. Pardon me. This results in a profile that looks like this, where we have time in lifetime in hours on the y-axis in green, and on the x-axis we have temperature. You notice that the temperature scale is nonlinear. This is because we're really plotting time or temperature in reciprocal temperature units, but I don't know about you, but I have a tough time thinking about materials in reciprocal temperature units, and so the software available will recast that axis into a temperature that we're more familiar with. And on the right-hand side, we have another time scale, lifetime scale, but one that is cast in more commonly encountered terms such as hours, weeks, years, and decades. The green line represents that line of thermal indices taken from the Krasanovsky equation. And at one particular point, a point of interest in this case, looks like it's about slightly less than a decade, we can draw a line and create from that, or pluck from that curve, the temperature that corresponds to that thermal index. It would look like here something like 340 degrees C. Now, once the kinetic method for determination of lifetime was developed, we wanted to correlate that with actual end use. And so the folks at DuPont were asked for, can you give us some examples of materials that for whom the thermal indices have been determined? And into our laboratory, John Blair brought a box of 40 some odd test specimens. We examined these materials by the thermogravimetric method and found that about 40% of the cases of an aging test and the thermogravimetric data agreed for activation energy and log of the pre-exponential factor, that is the thermal index, as in both methods. In about 40% of the cases, the activation energy for the two methods was the same, and we could fix the position on the curve with a single of an aging test. This produced the relative thermal index measurement from the Krasanovsky equation. And in about 20% of the cases, there was a disagreement between the of an aging test results and the thermogravimetric results. Now, in my naivete, I thought this was a terrible correlation. And it was only years later that I came to realize that for 80% of the cases, using a single of an aging test, we had a great correlation. And by the time that we came to this realization and wanted to put this relationship in the literature, our results had actually been purged from the laboratory by one of those record retention programs that were sort of the management fads of the 1980s, and the data had been lost. So this is a recollection, and you must consider it an unverified recollection at this place and time. Now that brings us up to where we are today. Today we have a new tool, not so new, it's been around for almost 20 years now, that is a tool that can aid in the determination of lifetime and accelerated aging, and it's modulated thermal analysis. On the x-axis we have time, and on the y-axis we have temperature. The straight line is a line that represents the underlying heating rate of the thermal curve, and the red line represents an oscillatory temperature around the underlying heating rate. This is the deep independent parameter in modulated temperature thermogravimetry. And when this modulated temperature program is imposed on a mass loss, we see that the derivative of the mass loss also has an oscillatory profile in it. When nothing has happened, the oscillations are small, but as we go through the peak of maximum weight loss, the oscillations increase. Now, looking at these curves, we can look at the top of one of these oscillations and the bottom of the adjacent oscillation and look at the rate of the kinetics at these two particular points. I mentioned a moment ago the concept of the general rate equation. This is that general rate equation in which the term on the left-hand side is the rate of reaction, and on the right-hand side in an exponential format is the activation energy and temperature, and there are some other terms in here that include Z, the pre-exponential factor, This is the rate of reaction at infinite temperature. And a term F of A, which is an expression that is called the model of the reaction. It is the form of the dependence of the reaction on the amount of material that's present. Now, this equation can be ratioed then at 2 points on the curve, at the peak of one of those oscillatory mass loss and at the adjacent valley next to it. And when we do that, some of the mathematics drops out and we create a new equation, which I'll get to in just a moment. But we can do this in a more mechanistic way. Rather than having an oscillatory temperature program, we can have a step change program. And this concept was developed by Joe Flynn and Brian Dickens at the National Bureau of Standards some years ago. They developed the equation which is shown here, in which the activation energy is proportional to the underlying temperature, that's the T value here, and A, which is the half amplitude of the steps that from one temperature to the other. This is the same value that is generated in modulated thermogravimetry, where we use an oscillatory temperature program. The difference between these two approaches is that because it's stair-stepped, the factor jump method can only determine kinetic parameters over the width of one step. In modulated thermogravimetry, because Fourier transform is used, the information is gathered continually and we get a continual presentation of activation energy. Now, the benefits for modulated thermogravimetry for thermal endurance measurements cause us to look to this tool as a primary tool for gathering accelerated aging tests, mainly because we have a continuous measurement of activation energy. This means that we can examine our curve and ensure that the region that we've chosen for our point of constant conversion, let's say the 5% mass loss, is a region of stability. The modulated thermal analysis experiment is performed in only a single experiment, while the Ozawa-Flynn wall approach requires at least 4 experiments and perhaps even double that amount. The modulated thermogravimetry avoids the time-consuming iterative process of having to work through the Doyle approximation to get our numerical value. It avoids the estimation of the integration interval, that's the Doyle approximation, altogether. And finally, from a more practical standpoint, it produces demonstrably better precision in the kinetic parameters that are generated. Because activation energy is in the kinetic expression in an exponential factor, the determination of the most precise measurements for activation energy leads to the best thermal index results. So where are we now? We have a series of ASTM standards for the determination of kinetic parameters. There is the standard E1641, the Ozawa-Flynn wall method. This is easily performed by hand, but is way more easily performed by the computer data analysis function. We have a new factor jump modulated thermogravimetric kinetic standard that's in development. We anticipate that this standard will be available sometime in late 2014. And we have a standard for the determination of thermal index from the thus derived kinetic parameters from thermogravimetry. So where do we go from here? Well, my experience with those that gaze into crystal balls and report on what they see is that what they see and tell us about is usually wrong. But this doesn't prevent us from going through the process yet again. And so if you'll bear with me, I see a few things that we might want to do in the future. There are a number of challenges or assumptions, as the case may be, to the determination of pardon me, activation energy, thermal indices from thermogravimetric data. The first of these, and it's the same concept that is associated with of an aging test, is that decomposition is related to actual lifetime. There's no data that I'm aware of where this correlation has actually been made. And there's been a reason for this up until now, basically that the polymers that we use in our everyday life have not been around long enough, by and large, to be able to verify their lifetime in many of the uses that we observe. But one would anticipate that organizations like Underwriters Laboratory might have enough data that they could create correlations between of an aging results and the actual lifetime of products. That might be something that we'd want to look into. The second assumption is that of the general rate equation. We have no reason particularly to believe that this is not true, but there may be some cases where it is not, and we probably will want to examine any special examples of where this might occur. Among the assumptions that are associated with the use of the general rate equation is the concept that there is a single decomposition mechanism. Now, the scientists who examine the decomposition of polymeric materials have examined them very carefully with tools like gas chromatography and mass spectrometry. And they tell us for sure that these are not a single decomposition reaction, that there are a variety of reactions that take place. But many decomposition reactions are governed by one or two typical reactions, or one or two reactions are in the main those that lead to our end results. One of the assumptions that we have for variable heating rate methods is that these reaction mechanisms are temperature independent. By and large, competing chemical reactions are not temperature independent. And so we would want to be very careful about our selection of kinetic processes so that the temperature effects are not large. Another assumption is that of the reaction being conversion independent. We know for many cases that this is not the case, but for lifetime testing this is probably not a problem because we select our point for end life very early in the mass loss process, and so we anticipate that these early conversions will focus on only one or two chemical reactions. A more difficult case to examine is that of oxidation. In actual practice, we anticipate that the failure for many polymeric materials is not decomposition itself, but is oxidation. And so any test for lifetime that doesn't include oxidation probably or possibly may have an error. We can test for oxygen and the effect of oxygen in thermogravimetry, but we have to take some special steps. For example, if we try to run our decomposition process in air as an atmosphere, there's enough oxygen in the air that the organic materials will, as the chemists of old used, will take fire, which means they burn. And this means that the energy of combustion is so large that it elevates the temperature of the test specimen. That is, it does not follow the temperature program upon which the kinetic experiment is based. So this kind of an example may be overcome by using lower levels of oxygen in our inert nitrogen. We've had some success in our laboratories of using 3% oxygen in nitrogen as a purge gas to examine the case where oxygen is present. Another example that might happen in the future is the addition of additional precision in the kinetic determinations or a simplification in the kinetic determinations based upon additional mathematics or mathematical models. This could provide more precise test methods, and the more precise test methods, the better off we are. Finally, the last challenge or assumption is that of the assumption of first-order decomposition kinetic mechanisms. This is the process that we most commonly use. It is the one that has been used in oven aging tests for almost half a century rather. But some recent work begins to show us that maybe there's some other things that could come into play here. In this thermal curve, I show you the polytetrafluoroethylene activation energy versus conversion plot. This is from some work by Gray Slough at TA Instruments. And you see that he's performed this measurement a series of times by the colors of the various thermal curves. But these profiles where we have activation energy on the y-axis and conversion, that is mass weight percent, on the x-axis, the activation energy changes a little bit throughout the decomposition mechanism. But it does appear to be repeatable. So the concept of examining materials and looking at their reaction mechanism is one area of current research. In our laboratory, we chose to look at some work on polytetrafluoroethylene based upon the method of Lei Qing from China. In this process, various kinetic models are measured against the variable heating rate data that commonly comes from the Ozawa-Flynn wall procedure. And we examine each model by looking at a term that's called the slope. If the slope is close to 1, then we have good agreement with the particular model, the model being the function of related to conversion. The second tool that we can use to examine the fit is the tightness, the smallness of the standard deviation of this determination. So if we look at this particular example for PTFE, and we look down at the fourth line down, we see that for the contracting length model, let's look at the one above that, the contracting area model, we see that the slope is very close to 1. It's 1.0. But the standard deviation is a little bit large. It's at about 7%. The order for the contracting area model is 1/2. Now if we look at the curve at the very top, the data line at the very top for the first order reaction, we see that the slope is 1.1, not exactly 1, but not unreasonably close to 1. But its standard deviation is very small. It's on the order of 2%. So if we look at the intermediate value of the contracting volume, we see that it has intermediate values for both slope and standard deviation. This means that of the three models, first order, contracting volume, contracting area, or if we call them by order, 1, 2/3, or 1/2, each of those particular curves could be used to illustrate the decomposition mechanism for polytetrafluoroethylene. Now the mathematics for the contracting area and the contracting volume curve are more difficult to use than the mathematics for the first order reaction, and so we're led back to the case that for PTFE, a first order reaction model would seem to suit pretty well. Kim and his co-workers in Korea have looked at a number of polymeric materials, including high-density polyethylene, branched polyethylene, polypropylene, and polystyrene, and they have observed models that look like contracting area, nucleation, and growth. These are terms for various dependence on reaction order, and they have a model, in this case, if you look at the F number on the right-hand side, a reaction order of 1/2, 2/3, 2/3, 2/3. And we saw from the previous case with polytetrafluoroethylene that any of the reaction models for first order are very close to that for other fractional order models for these materials. This gives us confidence that the first order model that we have traditionally used for these polymer decompositions is not an unreasonable assumption to make. But if we wanted to fine-tune the process, we could determine kinetic parameters more closely by using one of these other reaction models. So of what do we have here, 6 or so different kinds of challenges and assumptions. We've gone through most of these. We've examined them. They look like they are not unreasonable assumptions, and so we can have confidence in the art of using thermogravimetric data for the determination of lifetime parameters. I want to thank you for your kind attention here today.
Thank you, Roger, for that informative presentation.